Now that we have learned the identities for the sum and difference formulas of sine, cosine, and tangent, we're able to extend that to find the formulas that we refer to as the double angle identities. So in other words, let's say that we wanted to find sine of 2a. First thing to recognize is that 2a is really the sum of an a and another a, or the sum of the same angle. So in other words, to find sine of a double angle, we need to realize that 2a is the same thing as a plus a. So we can actually use that fact to our advantage because we know a sum formula for sine. We know that it's simply sine of the first, cosine of the second, plus cosine of the first, sine of the second. But since both of the angles are the same, notice that these are actually like terms. So sine of a cosine a plus another sine of a cosine a means that we have an identity for sine of 2a, which is simply 2 sine of a times cosine of a. So look at how this identity is going to benefit us. If we're trying to find sine of twice some angle, but all we know is information about the angle A, then we could rewrite this in terms of single angles, which will now allow us to evaluate the value of sine of that double angle. So we could do that same thing over here and recognize that cosine of 2a is the same as cosine of a plus a. And now we should realize that by the cosine formula, this is where we have cosine, cosine. So we have cosine of a, cosine of the second. And then remember, for cosine of a sum, that becomes a difference. And therefore, we're left with sine of a times another sine of a. And so this simply becomes cosine squared of a minus sine squared of a. And so again, if we are given a double angle for cosine, then we can use the information about the single angles in order to compute that. So now I'd like to just show that this is much different than something that this looks similar to. Okay, notice that this is saying that cosine squared of a minus sine squared of a is equal to cosine of that double angle, of the angle that's twice as much as a. Notice that that's much different than saying cosine squared a plus sine squared a, which is our Pythagorean identity. That's equal to 1. So be very careful with those, because even though these somewhat look similar, the fact that there's a minus sign here in between cosine squared a and sine squared a says that it's actually going to be the double angle formula for cosine. Okay. And lastly, for tangent, we have tangent of the angles a plus a. Remember, we also had a sum formula for tangent. And the way that looked was by saying tangent of the first plus tangent of the second divided by 1 minus tangent of the first times tangent of the second. But because, again, these quantities, these angles are the same, we could combine these into one single formula and say that tangent of 2a is the same as 2 tangent a divided by 1 minus tangent squared of a. And so all of these just turn out to be some special forms of the sum formula for sine, cosine, and tangent. So knowing these formulas, we're going to be able to use, as we mentioned, the single angles of A in order to compute all of these, since a lot of times we're given information about, say, 30 degrees, 45, 60-degree reference angles, but we want to find information about angles that are twice as large. And so There's a few other formulas actually that we're going to be able to find for cosine of 2a that are really derived from the Pythagorean identities. This is our starting point for our the first formula for cosine of 2a. We can actually use the Pythagorean identity cosine squared a plus sine squared a equals 1 to notice that cosine squared a is the same thing as 1 minus sine squared a. We could also see that sine squared of a is equal to 1 minus cosine squared of a, if I were to just subtract each of those terms to the other side. So with that shown here, we're going to be able to replace cosine squared a with 1 minus sine squared a, and possibly simplify this formula to a different form that might be easier for us to use. So let's replace cosine squared a with 1 minus sine squared a minus sine squared a. And now notice that I've got 2 of that same result of sine squared a. So this gives me 1 minus 2 sine squared of a. So sometimes this one is actually beneficial to use as well. I mean, if we've got one identity that says that cosine of 2a is equal to this form, that would require us to know both cosine of a and sine of a. But what if we only know the value of sine of a? Well, then this is a better form to use as opposed to using the first one. And likewise, we're going to be able to go over here and replace sine squared a with 1 minus cosine squared a. So we could do that same thing, going back up to the top. And we could keep the cosine squared a where it is. But now we say minus what sine squared a is, which is 1 minus cosine squared a. And now by distributing that negative, that gives us cosine squared a minus 1 plus another cosine squared a, which gives us 2 cosine squared a minus 1. So again, even though the original format for cosine of 2a is the difference between cosine squared a and sine squared a, sometimes if we're only given information about one function or the other, we can use any of these 3 options to evaluate cosine of 2a. Take a look at this first example. We can see that we're given a value of cosine of theta, which is 3/5. So I know that because cosine is positive, that means that the x-coordinate is positive. So that means that we're either in quadrant 1 or in quadrant 4. Now, we're also told that sine of theta is negative. That means that the y-coordinate is negative, so we must be in either quadrant 3 or quadrant 4. And so what we could tell here is that we must be in quadrant 4 because of the fact that both must be true. Okay, so the angle that we're given is in quadrant 4. But notice that we're trying to find sine of twice that angle. So let's just visualize what we're trying to look at this point. Okay, by drawing an xy coordinate plane here. Okay, so we know that cosine of theta is 3/5. So that means that the x coordinate would be about 3, the y coordinate would be 5. I'm sorry, the hypotenuse would be 5. So we would have something in the 4th quadrant that looks like this, where we would have an x coordinate of 3, a hypotenuse of 5. And so now the angle that we're referring to is right here. This is the angle theta. But what we're trying to find is the angle that's twice as much as theta. So let's think about where that would be. So 270 degrees is right here, and this is 360 degrees. So I don't know what that angle is that I'm referring to here, this the triangle with 3 and 5. But I do know that it's somewhere between 270 and 360. So let's look at what twice those angles are. If I take a look at 2 times 270 degrees, and then I look at 2 times 360 degrees, then that means that if I double that angle, I would be somewhere between 540 degrees and 720 degrees. So if you think about where that is, that just means that twice that angle is going to be somewhere in the third or fourth quadrant on the second rotation around. So when I look at the twice that angle, then twice that angle would look something like, here's the first angle, and if I double that, it would be somewhere, again, down here somewhere here, maybe it's a little further, I don't know where it is, but it's going to be somewhere in one of these two quadrants. So let's say maybe it's over here somewhere, I don't know. Okay, so if that's the case, then that would be referred to as 2 theta, and we're trying to find information about sine, cosine, and tangent of that double angle by just being given information about the angle theta. Okay, so that's the general idea of what we're trying to do here. Okay, so if I'm going to find sine of 2 theta, let's just keep in mind what our formulas are. Right, sine of 2 theta is the formula 2 sine theta cosine theta. So I'm going to have to know sine and cosine to be able to do this problem. Tangent of 2 theta is the same as tangent, or 2 tangent of theta divided by 1 minus tangent squared theta. So that means I'm going to have to know information about tangent theta in order to do this problem. Unfortunately, all I'm given is cosine theta, so I can't do either one of those yet. But notice with cosine of 2 theta, I've got all kinds of options. I've got any of these options right here. So this is a situation where, knowing that all I'm given is cosine theta, I might as well use the one that only involves cosine of A. So let's find cosine of 2 theta first, and maybe that would help us. So we know that cosine of 2 theta is the same as 2 cosine squared theta minus 1. But we know that cosine theta is 3/5. So what we're really doing is just taking cosine, squaring it, and then plugging in 3/5 to this spot right here. So now we can do the algebra and work it out. This becomes 2 times 9/25 minus 1. That's 18/25 minus 25/25, which means that we know the value of cosine of 2 theta. So cosine of that double angle is equal to negative 7/25. Well, think about what that means. That shows us that this angle, this right here, is showing us that cosine is negative. Cosine is negative in quadrant 2 or in quadrant 3. So now we know that not only is it somewhere in quadrant 3 or 4, but just by finding the cosine of the double angle, we know that the double angle is somewhere back here. Okay. But we're still running into an issue because that didn't help us with finding sine or tangent of 2 theta. So before we can continue on, we're going to have to know what sine theta is. So remember, we got a couple of options for this. One option is to use an identity that relates cosine theta and sine theta. So if I'm trying to find sine theta and I know cosine theta, then we can use the identity cosine squared theta plus sine squared theta is equal to 1. And we know that cosine theta is 3/5. So that becomes 3/5 squared plus sine squared theta is equal to 1. And now again, just by manipulating this equation, we can find what sine theta is. So that gives us a 9/25 plus sine squared theta equals 1. If I subtract 9/25 from both sides, that becomes sine squared of theta is equal to 16/25, which implies by taking the square root, the sine of theta is either plus or minus. Every time we take the square root of both sides, we can't forget that we're taking the plus or minus of that result, which means that my answer is plus or minus 4/5. But this is where we just have to realize that it told us up top that sine of theta was negative. So that must mean that my sine theta is negative 4/5. Okay. And that's one piece of information that we can use here. That's one way that we were able to find sine theta. Another way we could have found sine theta is just by coming over here and recognizing that this is y. And we're trying to find, using the Pythagorean theorem, what y is. And so we could have just said 3 squared plus y squared equals 5 squared. Subtract 9 from 25 to give y squared equals 16. Therefore, y equals plus or minus 4. And now we realize that this value over here is in fact negative 4. And from there, we could have found that sine theta is opposite over hypotenuse, which is still negative 4/5. There's lots of ways to do this, but the bottom line is we're trying to use this information in order to find sine of 2 theta. So let's find sine of 2 theta. So now our formula for that is sine of 2 theta equals 2 times sine theta times cosine theta. So that means that we're left with 2 times what the value of sine theta is times the value of cosine of theta. So since sine theta is negative 4/5, and we see the cosine of theta is 3/5, when I multiply those together, we find out that sine of 2 theta is equal to negative 24/25. And so again, that just validates the fact that my angle, because sine is negative and cosine is negative, that tells me that the angle that I'm referring to is again somewhere down here in the third quadrant, which should make sense based on the information we've had so far. So we've found sine of 2 theta and we've found cosine of 2 theta. So the last thing we need to find is tangent of 2 theta, which we could use the formula up here. The tangent of 2 theta is 2 tan theta over 1 minus tan squared theta. But there's actually an easier way now that we've already found sine and cosine. We should realize that tangent of 2 theta is simply sine of 2 theta over cosine of 2 theta. So since we found both of those, we know the tangent of 2 theta is equal to negative 24/25 over negative 7/25, which means that tangent of 2 theta, by multiplying by the reciprocal, is simply 24/7. And there's our result for all of our trig functions of the double angles. Okay, so notice that the sides of that triangle, obviously, the triangle involving 2 theta, would have sides of 7, 24, and 25. That's obviously different than this triangle over here that has sides of 3, 4, and 5. And that's because it is a completely different triangle in a completely different location, but we're being able to use all of our single angles here in order to compute the formulas for the double angles. In this next example, we're given an information about cosine of the double angle when we're trying to find information about theta itself, or rather the 6 trigonometric function values of theta. So the way that we can start by doing this is by thinking, how can I use the information that's given to me here, this cosine of 2 theta, in order to find something about a single angle? Well, remember, we have a few different formulas for cosine of 2 theta, right? We've got cosine squared theta minus sine squared theta. So we could set that equal to 4/5 and try to find cosine or sine. The problem with that is I've got two unknown trigonometric functions in that. So that's probably not the best form to use. So instead, why don't we use one of the other two, which is 1 minus 2 sine squared theta, for instance, and realize that that must be equal to 4/5. So we just replaced our cosine 2 theta with its formula, and now we can isolate sine theta to at least know this value. Okay. All right, so we can subtract 1. That gives us negative 2 sine squared theta. And if I subtract 5/5 from that, that gives me negative 1/5. Okay. If we divide by negative 2, that gives me sine squared theta is equal to positive 1/10. And now if I square root both sides, that gives me that sine of theta is plus or minus the square root of 1 over the square root of 10, or root 10 over 10 by rationalizing the denominator. All right, so we got sine theta at least, but now we need to know which one of these it is positive or negative. And that's where we use the information over here where it says that theta is in quadrant 2. Now keep in mind, in the acronym here for ASTC, that's a quick little way for us to remember what's positive and negative in what quadrants. Since we're in quadrant 2 here, we know that sine is going to be positive. So I know that sine is positive, which implies that cosine will be negative, tangent will be negative, secant will be negative, cotangent will be negative, while sine and cosecant are going to be the only positive results. So that means that we know sine of theta already, and therefore sine of theta is positive root 10 over 10. And now we pretty much can find all the rest simply by drawing a triangle and finding the rest. We could use the fact here that since we're in the second quadrant, we know that the angle is going to be somewhere here. So this must be our angle theta. And therefore, if we draw our triangle here, we know that the opposite side is root 10, while the hypotenuse is 10. And now we can find our information here. We can use the Pythagorean theorem in order to find x. And once we have that, we'll be able to find all 6 of our trigonometric functions. So the point of this was, let's start with a formula that we know for the double angle so that we could at least find some information about the single angle. And once we have that information, we could pretty much find everything else we need. All right, so let's go ahead and do the Pythagorean theorem. We get that x squared plus the square root of 10 squared is equal to 10. That tells me that x squared, 10 squared, I'm sorry. That tells me that x squared plus 10 is equal to 100. So x squared is equal to 90. So I know that x is equal to the square root of 90, which is 3 root 10. Now technically it's plus or minus, but we know up here that this is back into the second quadrant, so x must be negative 3 root 10. And we're ready to just start filling in our gaps here. So we know the cosine of theta is the x value over r, so negative 3 root 10 over 10. We know tangent of theta is opposite over adjacent, so I know that that's root 10 over negative 3 root 10. and the root 10s cancel. So we're left with negative 1/3. If we take the reciprocal of each of these, we know the cosecant of theta is 10 over root 10. But if I multiply by the reciprocal, that would give me root 10. If I look at the reciprocal of cosine of theta to get secant of theta, that's going to be 10 over 3 root 10. But same idea, if I rationalize the denominator by multiplying root 10 over root 10, okay, that gives me 10 root 10 over 3 times 10, where the 10 cancels, and we're left with root 10 over 3. And finally, cotangent of theta is just the reciprocal of tangent theta, so we know that that's negative 3 over 1, and therefore negative 3. So all we needed to know was one piece of information about the double angle, and we can use one of our identities or one of our formulas in order to find information about the single angle. The last identity that I want to talk about here, or the last type of problem I want to deal with, is verifying an identity. So notice that identities could also include double angles. And so if we want to simplify this, then we need to be able to figure out, should I start with the left side and try to turn it into the right? Or should I start with the right side and try to turn it into the left? Now you really could start with either one, remember, with identities. So I'm going to think that there's probably more to do when I have more functions, as opposed to trying to figure out how I could change 1 and cosine into cotangent and sine. So I'm going to start with the left side. And so let's start by recognizing that cotangent x can now be multiplied by the double angle formula for sine of 2x. So 2 sine x cosine x. Now the reason I thought to do that was, well, I saw a double angle, so I always like to work with the single angles in general. But I know that some may be thinking you always have to keep in mind what the goal is. And my goal is to make this turn into 1 plus cosine 2x. So it might seem a little peculiar to change the double angle over here since I end with a double angle. But I'm going to guess that by doing this process over on the left side, I'm going to be able to get something that involves the double angle formula for cosine, so I'll be able to recognize that later. So I can't really see what to do yet here, so why don't we use a quotient identity to change cotangent x into cosine x over sine x. Okay, and that's still going to be left with 2 sine x cosine x. Well, notice at this point the sine x can cancel from the numerator and denominator. So all we're left with here is 2 cosine squared of x. But again, I'm always trying to keep in mind my goal. Remember, my goal is over here. So I'm trying to get it to look like cosine of 2x. So I'm going to just write an identity just to remind myself what we're doing here. And so remember that the identity for cosine of 2x, there's a few of them. But notice that I'm already in terms of cosine. So remember that the identity is 2 cosine squared x minus 1. So look at how I have a 2 cosine squared x here. Then notice that I could automatically recognize from my Pythagorean identity, or from my double angle identity, is that 2 cosine squared x minus 1. I can add 1 to both sides and notice that I'm left with what the right side is supposed to be. So I'm left with 1 plus cosine of 2x from the double angle identity. And so notice that anytime you have a double angle, most of the time, the best course of action is to change that double angle, or that trigonometric function of the double angle, into single angles by using one of our identities to make our process a bit easier to deal with. So now that we have learned the double angle identities, what about something that involves a triple angle? So it's not as if there's a particular formula for a triple angle, but what we can recognize is that this looks like the sum of 2x and x. Now the reason why I would write it like this is because when I apply the sum formula on this, on this sum, I'm going to be involving double angles and single angles. So this would be sine of the first times cosine of the second plus cosine of the first times sine of the second. And so now that I've broken apart this triple angle into double angles and single angles, my goal now is to convert it only in terms of sine x, which means I can't have this because that's not a sine x. I can't have that, and I can't have that. So I have to find some way to convert these. So I'm going to go ahead and use the double angle identities on each of these. And sine of 2x is 2 sine x cosine x times the cosine x that's already there. Plus, and now I see for cosine of 2x, again, I have options. But because I'm converting it purely into sine, I'm going to use the one that only involves sine x. So I'm going to write this as 1 minus 2 sine squared x times sine x. So if we distribute, we're getting a little bit better, but we still see a few cosines here. So this becomes 2 sine x times cosine squared x plus sine x minus 2 times sine cubed of x. So we just distributed the sine x to each of those. So it looks like we're almost there again, but we're not quite there because notice cosine squared of x needs to be changed into sine of x as well. So why don't we use our Pythagorean identity, recognizing that that's 1 minus sine squared x. And now I see everything is completely in terms of sine x at this point. So we're just going to bring everything else down and simplify until we could find the value of sine of 3x. Okay, so if we distribute this, notice that we distribute 2 sine x to here, and we distribute 2 sine x to here. And let's see what happens there. So here we get 2 sine x minus 2 sine cubed of x. But when we drop down these extra terms, we realize that we have a few like terms. The sine x terms can combine and the sine cubed x terms can combine. And therefore we could see that the value of sine of 3x, which was what the original goal was, is the same thing as 3 sine x minus 4 sine cubed of x. And so let's just keep in mind again what the goal of this is. Whenever you're dealing with a multiple of some angle, sometimes it's harder to deal with because I don't know information about the triple angle. So it's often easier to convert into trigonometric functions of single angles, and that's what our goal was here. So even though the right side looks a little more complicated, it's often easier to compute because we know information about that single angle.